Okay, section 2.4 are graphs that enlighten and graphs that deceive. In this section, we're going to look at a variety of different types of statistical graphs, and the objective here is to identify a suitable graph for representing a set of data. The graph should be effective in revealing the important characteristics of the data. Not all graphs are created equal, and it is possible to intentionally deceive the public by abusing what type of graph it is that you use. Some graphs are bad in the sense that they contain errors. Some graphs are bad because they are technically correct but misleading. And it's important to develop the ability to recognize bad graphs and identify exactly how they are misleading. One of the first graphs we're going to look at is a scatter plot or a scatter diagram. In a scatter plot, we plot ordered pairs, x comma y. And I know x's and y's are scary because that reeks of algebra. You do have to know a little bit of algebra, but we're going to let the calculator handle a lot of the number crunching for us. In the scatter plot, we have a horizontal axis here. Typically, that's your x-axis. Whatever is listed first here is the ordered pair. That's what's going to be plotted along the x-axis. And then our y-axis is the vertical axis, and whatever variable you list second, or we're going to be using list 2, is going to be plotted along this axis, the vertical axis. Any point that you have selected, it can be uniquely represented by a set of ordered pairs, x comma y. So this point, just kind of estimating, it corresponds to about, what would you say, 117 maybe on the x-axis and maybe 39 on the y-axis. So that point would be 117, 39. Y'all remember plotting points in algebra? So this graph here represents randomly selected males. The pattern suggests that there is a relationship between the waist circumference measured in centimeters and the arm circumference measured in centimeters. We say that there does appear to be a pattern because we see this general upward trend of things. As the waist size increases, it looks like the arm size is also going to increase. Here's an example problem that we're going to go through, and I'm actually going to show you how to do this on your calculator, how to create a scatter plot on your calculator. So get your graphing calculators out. We're going to be ready to use them. The instructions say to construct a scatter diagram using the data table to the right. This data is from a study comparing the amount of tar and carbon monoxide in cigarettes. Use tar for the horizontal scale and use carbon monoxide for the vertical scale. Determine whether there appears to be a relationship between cigarette tar and carbon monoxide. So what we're going to do is we are going to get our calculators. Here's my graphing calculator. The first thing you need to do is turn your calculator on. So I hit the on button right here. To put data into a list in your calculator, we're going to hit the stat button. Does everybody see the stat button right here? Hit stat. And then we're going to edit our data right here in this list that says edit. So we hit enter. Now I've already typed my data in. In list 1, we're going to type in all the tar. In list 2, the carbon monoxide. So we do this going down. So I typed in 16, type 16, and then hit enter. 13, enter. 1, enter. 10, enter. 5, enter. And then we jump over to the next column, 17. So we type in 17, enter, 8, enter, 9, enter, 18, enter, 10, enter, and then we jump over to the third column. That's the way you read your data. I would appreciate it if you would go ahead and practice this. This video will be up later for you to look at. If you have your graphing calculator, pull it out and type in these numbers into your calculator. Use the arrow key right here to scroll over to the next list, and that'll be list 2. And in list 2, go ahead and enter the numerical values for the carbon monoxide. Okay, if you want to clear out the data that's in a column, let's say that you put it in list 3 and you want to clear it out. Let me just put some numbers in here. If you put your numbers in a wrong column or you entered a wrong number, what you're going to do is you're going to go up to the list name. That's at the very top. You see how the cursor is up here on the list name? Here you hit clear, and the numbers went away right here, but hit enter and it actually deletes all the numbers from the list. Well, here's what we're going to do. Once you get your data entered into the calculator, you want to quit this program. So we hit second mode, and that takes us back to the home screen. And then we want to do our plot. And it's a statistical plot. So you see how it says stat plot in blue? Yours may have it in yellow. So in order to access, for me to access anything in blue, I hit second, y equals. And this brings up a screen for our statistical plots. Second, y equals. If you have the newer operating system, it will look a little more polished than what mine looks like. And some things may look slightly different. We'll have to play with that. But in general, what I'm doing is going to look similar to what you have at least. So second, y equals. You notice plot 1 is turned off. The first thing we're going to do is turn this plot on. So we're going to hit enter. And it brings up plot 1. You know this is plot 1 because plot 1 is highlighted. And we hit enter again to turn that plot on. It's just a toggle. If you want to turn it off, move the cursor over to off and hit enter. If you want to turn it on, put the cursor on the word on and hit enter. Then we hit the arrow down to go to the different types of graphs. And the first type of graph that is highlighted, this is going to be our scatter plot. This is what we actually want to look at. So we're going to go down to the X list. If you put the tar data values in list 1, that's what you're going to use for the X list. That's your horizontal axis. The X-axis is the horizontal axis. And list 2 then would be your Y list. They have a choice of 3 different markers here. These are for the blind people over 40. If you're in your 20s or 30s, you could probably handle the plus mark and see it. If you're a teenager, you could probably handle just the pixel mark and still see it. I'm over 40. I'm going to use the little box for my markers. So every time I have a data point, it's going to put a little box. Now, I don't want to worry about how to scale the axes. So there's a real cool tool. Hit the zoom button, and if you go to zoom 9, I just hit the arrow up to get this screen. If you hit zoom 9, it will automatically scale your X and Y axes so that it gives you the best window to plot all the data. Looking at this picture now, there appears to be a positive correlation, which means as the amount of tar increases, the amount of carbon monoxide is going to increase as well. And you see how looking at a list of data in a table, this relationship is not as clear as it is by looking at the graph of the scatter plot. Moving on then to time series graphs. Time series graphs are graphs of data that have been collected at different points in time. I won't be asking you to create a time series graph, but you would be expected to interpret them. Here, this graph represents the Dow Jones Industrial Average high by year. What approximately was the Dow Jones Industrial high in 1995? If I ask a question like that, we'd go over here to 1995. We would trace straight up, and it looks like that was about 5,000. So in 1995, the Dow Jones Industrial Average achieved a high value of about 5,000. The Dow Jones Industrial Average is a measure in general of how your stock investments are doing. The higher the number, the better the investment. So you can see how much it's grown over time. When you see any sharp downward turns, that usually means we've entered a recession. And long about, this was 05, 6, 7, 8, about 2007, 2008, we started entering a recession. The economy started doing badly. So that's how you can look at a time series graph. We had a little hiccup right here where the Dow Jones Industrial Average dropped, guessing, let's see, that's 85, 86, 87 to 88. I think that's about when the first Gulf War happened. Is that right? So that's about the time that we first entered the first Gulf War, somewhere around there. So the conditions were getting bad, and the economy reflected that. So that's how you can use a time series graph. A dot plot consists of a graph in which each data value is plotted as a point or a dot along a scale of values. Dots representing equal values are stacked. So whenever you see a stack like this, what that means is these dots right here, there's a total of 1, 2, 3, 4, 5 data values that were exactly the same. You just stack them up. And this is kind of cool because you can see a representation of the shape of your data. And we're going to learn later on that the shape of the data, or have we already talked about the shape of the data? It's very important. It looks to us like, or it looks to me like this may be somewhat normally distributed, or maybe even trimodal. Looks like we have a peak maybe in 3 different places here. So it's just another way that you can analyze data. A stem plot or a stem and leaf plot is kind of like a dot plot, but instead of looking at dots, we maintain or we preserve the actual data values, and we can still see the shape. This distribution here looks to be symmetric and unimodal. What did we call that last time when we said we had a distribution that was symmetric and unimodal? Normal distributions are symmetric. The difference between a dot plot and a stem and leaf plot, we actually can see what our original data values were with the stem and leaf plot. The way this works is this vertical line here separates the stem part from the leaves part. And the way that we would look at this data, if I asked you to write down all of the data values here, the stem part represents the tens unit. The leaves are the ones units on your data. So if I asked you to make a list of the data that created this stem and leaf plot, you would start listing numbers 50 because of the 0 here. What would my next number be? 56. What would my next number be? 70, 72, 73, 74. We're getting 70, 72, 73, 74, 75. And then we have how many 76s? 5 of them. So you get the idea. On the stem and leaf plot, you can look at it and see what the actual data values were, as opposed to the dot plot, where if these are not measured in units of 1 here along the tens, or if you can't tell exactly what these numbers were, you lose your data values. So the stem and leaf plot is actually a stronger graph than just the dot plot, but you can still see the shape of the data. Next we have a bar graph. Bar graphs are used with qualitative data or categorical data. Remember, we talked about histograms last time. On a histogram, the bars touched, and that was quantitative data. On a bar graph, the bars do not touch, and it's qualitative data or categorical data. You can represent two categories on the same graph. Here's an example of a multiple bar graph, where the blue bars represent the median income for males by year, and the pink graphs represent the median income for females by year. The median income here is measured in thousands of dollars. You can see that males are earning more typically, and male incomes are on the rise. Female incomes are also on the rise, but the gap between them is becoming more significant. This graph doesn't tell you why that's occurring, it just says that it is. Then that opens up a whole bunch of questions for researchers to look into what could be the possible causes. Are males in higher positions or more upper management positions, and females taking a lesser role and staying at home with the kids? There's been a trend towards stay-at-home moms, whereas we'd kind of gotten away from that in the 70s. Moms went to work. Now moms are wanting to stay home with the kids. You know, that would affect the median income. Are we looking at differences due to education? I don't know. There's a whole bunch of information missing from this graph, but it does bring up an interesting point, but we didn't say why it's happening. A Pareto chart is a bar graph where the bars are arranged in descending order. On a Pareto chart, you still have categorical data. Our categories down here, what contributes most to happiness? These are categories: family or life partner, friends, leisure, work, study, music, sports. These are the things that cause happiness according to percent. The percent is on the vertical scale. The bars are touching here, but this is not a quantitative data. This graph does not represent quantitative data. It's a Pareto chart, it's still categorical data, but the bars touch like they do on a histogram, but the only reason the bars can touch is because it is descending. We don't work a whole lot with them. I just thought I would mention them. Pie charts. You guys have seen pie charts probably since middle school. I think if you come through the Texas public schools, we use a lot of pie charts and test with the standardized testing. So it's a graph depicting a qualitative data as slices of a circle. So we're looking at categories again. Qualitative, remember, means categorical, in which the size of each slice is proportional to the frequency count. This pie chart here actually represents the same information as this Pareto chart. Different graphs give you different feels or different feel for the data. On the Pareto chart, it was obvious that the family and partner contributed most to happiness, but on the pie chart, it's easier to see. or it makes more of an impact. Frequency polygon is another thing that you may look at. It uses line segments that connect to points directly above a class midpoint value. Now, a frequency polygon is used for quantitative data. Class midpoints, remember, are the middle value or the average value between the lower class limit and the upper class limit of a histogram or frequency table. So these dots here would represent the midpoints of your various classes, and then you just connect the dots with a line segment. A relative frequency polygon, instead of using count here or frequency as your vertical measure, relative, when you see the word relative, it means you're switching to a percent. So here's a graph that represents IQ scores using a percent, so it's a relative frequency for the group with high lead exposure and a group with low lead exposure. We expected to see lead. We've been told all of our lives lead affects the IQ of children if you're exposed to lead at an early age when you're developing. So look, this maxes out. The low lead group has a greater percentage of people with lower IQs in it. We're not surprised by that. Ogive is a line graph that depicts cumulative frequencies. When you see the word cumulative, I want you to think accumulate. So an ogive will start at 0 and it will end at its maximum value because we see these accumulating. This is like a cumulative frequency table. And then we have graphs that deceive. And we saw this before earlier in chapter 1, I believe, when we were looking at data. These graphs actually represent the same thing. These are bar graphs because the bars are not touching. This graph represents the highway fuel consumption that's measured in miles per gallon for a Honda Civic, a Chevy, and a Toyota. We have the same categories over here, highway consumption and miles per gallon. Which one of these graphs makes it look like the Honda Civic has way better gas mileage than the Toyota Camry? The one on the left or the one on the right? The left. What about this graph? If it represents the same information, what about this graph makes it so outstanding? It starts at 30, so you're only seeing the top part of this graph, and it exaggerates the difference between things. Advertisers do this all the time. Be aware of it. If the scale doesn't start at 0, it's easy to mislead with the information. They're both valid, but one is deceptive. Pictographs are another thing that you have to be aware of. On a bar graph, the width of the bars are the same, so we're only measuring along one dimension, and that's the height. So if something is double something else, here it looks like this actually is like 4 times greater than the height of the Toyota Camry. But when we're talking about a two-dimensional picture, not only does the height change, the width is going to change. If it's a 3-dimensional picture, things increase not by a factor of 2, but actually by a factor of 8, because we have changes along the length, the width, and the height of the graph. So here, this is a pictograph that represents people's pay based on their education. So if you have no high school diploma, this is the amount of money that you can expect to earn on average. Let's look at a high school diploma. This is the amount of money you can expect to earn. It looks like 18 times 2 is 36. This box here looks to be twice as big or hold twice as much as this box. But it's only because of the dimension change. If you double each side of a square, the area doesn't merely double, it increases by a factor of 4. If you double each side of a cube, the volume does not merely double, it increases by a factor of 8. So what you're doing whenever you use a 3-dimensional picture is you're exaggerating the difference once again. 74 divided by 18 is 4, roughly. I'm going to put approximately 4. This should be 4 times this. But look at the picture. That picture looks way more than 4 times. It looks to be 32 times bigger. It looks like you could earn 32 times more by having an advanced degree as opposed to no high school diploma. Do you see how the exaggeration is? Whereas if we would have looked at the same information on a bar graph, we would have seen a more fair representation. So pictographs using areas and volumes can be very misleading. This is actually the true results right here using a bar graph that are not misleading. So we can see that the difference between no high school education and an advanced degree is a little more fairly represented. So it's fair, objective, and unencumbered by distracting facts. That's what's necessary in order to have a graph that would enlighten or give you information as opposed to intentionally mislead you or even unintentionally mislead you.